So just to lay out the issues, again, the loss of information at our horizon is either an optical or physical phenomenon. If it's physical, people disappear by walking over the curve. If it's optical, people disappear by the angular resolution limit of the observer. So option 1, the ground is brought to eye level. The person walks straight away and disappears bottom first from things getting smaller with distance and an angular resolution limit. Option 2, the eye is brought to ground level. The vanishing person is represented orthographically without a regard to things getting smaller with distance and perspective, and your focus continually shifts downward to observe them going over a curved surface and vanishing coincidentally at the same rate as the angular resolution limit of the eye at 3 miles. After reviewing the above options, we will see how the optical angular resolution limit of the eye was replaced by the physical curvature of Earth, and we will then use that limit to calculate a sphere with a radius of 3,959 miles to 3,978 miles. The assumptions: perspective changes with the observer. Objects get smaller with distance. We've covered those up to this point. Small objects disappear from vision. So again, we've covered those within the first 3 of the series, and as well as the horizon rising to eye level. Our objectives, we've outlined these before. We are now in part 4. And so last time we discussed angular resolution and area patterns and Rayleigh's criteria, diffraction limits, angular size stability of the sun and moon, the cause of a sunset, the importance of Polaris with regard to distant vision, and the effects of magnification. We are now going to cover the inferior mirage and the horizon refraction across bodies of water, and a summary of the angular resolution limit. Over the next couple parts after this, we will discuss the globe theory and derive the Earth's radius in a couple of ways, and we will also look at empirical evidence and of deception of biblical significance. So let's talk about the inferior mirage a little bit. You may have noticed an inverted reflection from the last video about where the true horizon line may be as far as with regards to a sunset. So we'll explain that phenomenon here. So the inferior mirage, depending on atmospheric conditions, an inferior mirage is sometimes seen below the horizon or eye line. This represents the light bouncing upward to strike your eye inverted as a reflection. If conditions warrant, the viewing angle of the information below your eye line, which is the bottom 50% of your vision, is receiving light from an object near the resolution limit or the horizon. Like skipping a stone, the light received by your eye across distant water is hitting an atmospheric vapor layer that is less dense and bouncing up to meet your eye, instead of you seeing the light radiating from the water in a straight line. So you never see the water that's there within this mirage zone. Instead, you see the light above it inverted and sent to your eye like a mirror. The light that was supposed to reach you could not penetrate the layer, and so instead you view the light that met a critical angle of refraction and reflection from above. So from a perspective view, there still exists water within this inverted zone. You're just resolving the light bouncing off the sky above instead, rather than the light coming off that faraway water at a shallow angle. So if you were to increase your observer height, this layer shrinks away to reveal the water underneath, because the light from the further out water now has a more direct line to your eye through the medium. So again, here in the orthographic view and converting it down to perspective, on the left you have no visible vapor line there or vapor layer, so the water and the sky meet without reflection at the eye line. And then when we put this vapor layer in, still maintaining the same observer height, what ends up happening is there's water still present in that zone within perspective, not necessarily in reality, but within perspective, because the floor has been brought up to meet the sky, but the water is still present within perspective below that purple line. But you're going to see the mirrored sky there instead now in the presence of this vapor layer. We'll discuss that here. So to account for some distant observations that should not be seen on a globe, some will claim that in addition to the inverted images below, the upright versions of above these mirages are mirages as well. So they are like an inversion the inverted portion is fake, and then the upright version above is also fake, and that we're seeing what's called a fata morgana, which is essentially inversions on inversions. But you can video the same object linearly diminishing as it should without distortion as it travels. In other words, this is a real boat. It is the boat. It's not the mirage effect of one. So again, here's an example of a boat coming into view. You can see the inferior mirage, which is i.e. a reflection, like we'll talk about here in a minute, occurring at various points along the way as the boat travels away. So I've outlined the purple horizon line, or the potential true eye line. Again, the water would still be below this line with different atmospheric conditions, but it now looks like the inverted sky above as a mirror. And then the yellow line represents where the inversion is taking place as this boat is traveling further away within that water. So you can time-lapse these and take the points of where the inversion starts, and your actual true horizon line is higher up and further away. And then you'll see this visible false water line where the water starts to become indistinguishable and those shallow angles start hitting your eye. You'll have this visible false water line form. So if I take some of these pictures out and put them down here on the bottom, if our sun was setting, let's take the picture of our sun and place it within this view. Let's say the boats are sailing off at sunset. You would see the sun set at a slightly higher level than where these boats are, and I've kind of placed them there where it could possibly be. And so what's that saying is that again, because of how perspective works, and that we've already talked about what a sunset is, so again, the sun is hitting that lower compressed visual field line, that lower resolution limit, since your vision has been compressed against the floor, in this case the water. And when that high object above sets down, it will set into the true horizon line that you are viewing. It's the most distant, largest object. And so it would set higher than where these boats are having their inferior mirage. So again, just like these are actual vehicles, these are actual boats. So this whole Fata Morgana effect, that you're not seeing a real, a true image, that these are inversions on inversions, is just not true. This is a natural phenomenon when there is a less dense layer of heat between a dense water layer and a dense colder air layer. And so there's an actual dog in the picture in the upper right there, and that's an actual boat. And again, these are actual vehicles traveling towards you, and so forth. This is all the same effect. So let's talk about that a little bit. So let's return to our diagram to explain things. If we zoom in on this orthographic view, we'll see that this phenomenon is what's called a total internal reflection. So the vapor layer over the water is less dense than the air above and the water below. Essentially, you have a more dense, less dense, and then more dense layer. Snell's law says that when light travels from one medium into another, the difference between the incident angles of the ray is dependent on the difference between the indices of refraction of the mediums. So when the incident ray at theta incident, theta I we'll say, travels from more dense to less dense, the angle from the normal line, which is that vertical dotted line, gets larger for the refracted ray as it exits the medium or enters the new medium. And so we'll call that theta RA, or for theta refracted. When this angle reaches 90 degrees, when you rotate the incident ray, it will come off at shallower and shallower angles. Let's say we're looking down at the lower left diagrams here, where the water blue is below and the green vapor layer is above, so the very corner left diagram. So as the angle goes from the water in the more dense to the angle or to the medium that is less dense, you see that refracted angle is more shallow, and as we rotate that angle within the water and make it more shallow as it exits the water, it's going to get more and more shallow as well as it enters into that vapor layer. And there's going to be a point where between the normal line and the refracted ray is going to be 90 degrees. So that's called the critical angle. So between the dotted line and the yellow line, that's horizontal in the middle diagram there, on the lower left, is the critical angle. So when that's reached, you don't receive any light. Let's say if you were above the water line, the light ray would essentially skirt along the top of the water, and then any further shallowness to that incident ray results in what's called a reflection or total internal reflection, and that light is just then reflected back down at the incident angle with which it entered. So again, so when we have this 90-degree angle, we have reached a critical angle, theta critical, and any further enlargement in that angle results in the ray being unable to travel in the less dense medium. Bounces inverted off the interface between the two mediums, and total internal reflection occurs at the same angle as incidence. So the point where theta reflection is equal to theta incident. So I can take that water and vapor layer example, and I will invert it to become the more dense air layer, colder air, and then the less dense vapor layer below it. And the same phenomenon occurs, but inverted. And then I can take these two and stack them together, and I have a more dense, less dense, more dense medium. And we will then place that within our view to see how it is that we are seeing a total internal reflection. So when this occurs, you no longer see the water. Simultaneously, the air above this layer is also more dense, like we talked about, so the same thing occurs, and we just stack them on top of one another. When we combine the effects, we create a series of reflection points from near to far, where the near reflections are further below the horizon, and the further reflections are closer to the horizon line. So again, as you continue to do this, the further reflections that are occurring are going to be more near the purple line, your true horizon line, and the more near reflections are going to be more near the water line, or the apparent water line, where you stop becoming refracted rays, or just rays coming off the water, and they started becoming internally reflected, and you're not seeing them anymore. So again, from our orthographic view, we're going to rotate the ceiling and floor to meet at the vanishing point like we've done in our previous examples. And you can see I've drawn out some of the rays as to how they're acting within the black rectangle within that middle diagram. I've rotated this segment there on the right to kind of mimic a little bit about how these angles are being reflected from one another, and you can see how the angles from the water are being reflected downward. You're not seeing those angles any longer, but you are seeing the angles that are now at a more favorable angle to reach your eye, and that is why you're seeing the inverted sky above you. So again, when we rotate the floor to the ceiling, we only see the reflected rays from near to far from the sky, like the vapor layer has become a mirror essentially. When the reflections cease, we have the true horizon point where the sky meets the ground. If an object like a boat travels away from you within this layer, it will appear to ascend within it toward the horizon line and gradually disappear within it. The boat disappears bottom up as though the inferior mirage is gradually climbing upward over the boat, because more and more of the bottom of the boat is being reflected back to you with distance. Nearby, the bottom is seen because those rays can penetrate this layer. As the boat travels away, those rays coming from the bottom of the boat are increasingly reflected away, and you are left with the rays coming from the top of the boat, their reflection underneath, and the mirrored sky. It is as if the boat is swallowed up, bottom up, with distance. But keep in mind, your true horizon is above this mirror zone. So again, as the boat in the orthographic representation on the bottom is traveling straight away from you, it is traveling through more and more of this layer, and it is getting increasingly difficult for the bottom of the boat, which is has a much less density than the top of the boat in relation to this layer, because this layer gradually increases in density as it goes up. You're having a much harder time viewing those bottom aspects as it continues to travel away from you in a straight line within this layer. So as I rotate this view within perspective, you can kind of see how those boats would represent in an orthographic presentation, and they continue to travel within this vapor layer, and they will get swallowed up, essentially bottom up, as they approach your horizon line. And they may actually disappear before they actually reach your true horizon line. So if you find this, like let's say you have distant mountains in the background or something to that effect, you can look for the mirror point on them, and that will represent your true horizon line a little bit better than nearby inversion points. So when looking at long distance photography, arguments over whether the bottoms of the objects should be seen or not should take a backseat to observing the tops, because there is simply too much distortion near sea level to make sweeping claims unless the refraction is at a minimum about especially the bottoms of the boats. Why can't we see the bottom and so forth? It's just not relevant, because there's simply too many atmospheric effects across these bodies of water to make any sweeping claims. So as an example, if we now ripple the water, you'll see the lines expand and contract. Concentrate between the 1 and 2 centimeter marks, and you'll see it kind of move up and down and expand and contract. The millimeter marks will get closer together and further apart. Sometimes the ruler is longer, sometimes it's shorter, sometimes the numbers are closer, and sometimes they're further apart. So if we make our water waves a lens and the ruler a building, you can see how the floors within that building would distort. So I'll play it really quickly here. I'm just kind of tapping my finger through the waves, and you can see the effect ripples across the ruler, and the ruler distorts, changes shape. In general, the ruler stays within the same position, but the things within the ruler get distorted. So it's essentially as if we were looking through a lens. So I'm going to, if you look at this Skunk Bay time-lapse video, pay particular attention to the water that's right next to the land, and watch how it rises and falls, and you see an inversion there briefly, and then but look at how compressed the buildings get, and then they decompress. In general, they're staying in the same position, but the water line and some of the most of the time the land and the distant mountain are brought lower within your vision, not necessarily brought higher from when there is less refraction. So when you have a very clear image, you can take that as kind of your baseline, and then you'll see that most of the times the land will decrease or move inferiorly from your vision when that happens. So and that phenomenon is upward refraction. We'll talk about that. So again, sometimes you view the water meet the eye line correctly within this time lapse. Sometimes you see an inverted reflection. Sometimes refraction pulls the distant object lower, and it seems sometimes higher, although it's a relative higher. So in other words, when you see a very low compression image, like the one that I've labeled there, where it seems very crystal clear, and there seems like there's very little compression of the buildings differentially and so forth, you can kind of use that as a baseline, and more often than not, the buildings when compared are brought lower in comparison to that point. And same thing, you can look at the distant mountain within those views, and you'll see that it almost never gets raises up in height. It almost always gets dropped lower. And then below we have some oil rigs that were filmed, and you can see again that the distant rig has been brought lower down in comparison to the more close by rig. And by correlation, the water does appear to be brought higher, but again, you can see that multiple times within the time lapse, as the water does tend to move up and down based on the turbulence of the water and any number of effects. So we are getting a lensing and refraction effect through many different layers of vapor, sea aerosol that are subject to air currents, temperature, humidity, pressure gradients, and so forth. So to see the effect of this lensing, let's take another look at the Skunk Bay time-lapse stills and see what we can determine here. One thing I want to make clear is look at how you can see the mountain much better during sunset, and that's because those reds are less refracted away. They experience more diffraction, but we're not experiencing a diffraction limit at this point, like we talked about in part 3. So you're seeing the reds through the atmosphere a lot more than you're seeing the blues. The blues have been scattered out. And so you're essentially seeing a little bit further distance with the reds, just like you see a little bit further distance with infrared. And so when that happens, you can see that the mountain is at its baseline height, essentially. And as you compare it to some of the other frames, when you had a little bit more warmer air during the day, potentially, you see that the building in the mountain was brought lower. And again, that is upward refraction of that mountain. Again, your eye assumes straight lines, as we'll get to, and it brings the distant object lower than where it is at its baseline. But again, in general, you can see this kind of wavy appearance of things if you look at the lighthouse that I've pointed out in yellow, the yellow arrow, and then the apparent water line in the blue, and then the mountain in the background in black. And you can see how their relative positions to one another change with just a time lapse throughout the day. And so it is very difficult to make sweeping claims about how high things should be and low with pure numbers based on viewing an object across water. It's as if we're looking through like a wavy lens of distortion, like how I've outlined in the bottom. And so just keep that in mind when you're evaluating these long-distance photography shots across water. But for the most part, across water, the warmer water from the specific heat of water is going to be creating this warmer atmospheric layer above the water, and you're going to be creating a lot of upward refraction and pushing things in the background lower than where they actually are. So we'll talk about that here. So refraction over water is almost always refracted upward. The specific heat of large bodies of water keeps the air above the surface relatively warm and stable in comparison to the colder air higher up. And again, video link in the description. For almost all observations across vast distances, the warm air below and the colder air above create upward refraction, and objects are brought downward from the top. So again, you almost always see buildings appear lower than where they actually are. And so I've kind of diagrammed that here, what's happening with the prism. You have the colder, denser air above, and you have the warmer, less dense air below. And as the light rays are being reflected to your eye from those distant objects, they are getting bent upward to your eye. And so what you end up doing is creating straight lines from those rays, from your eyes extending back to the object, which is the black dotted line, and you are bringing that building or whatever you're viewing lower within your view. So when we view laser experiments, let's say, or laser observations across bodies of water, you'll see that they are refracted upward. And that is just the nature of that warmer air creating a less dense layer above the water. So as a way to kind of summarize this, you get more refraction with colder temperatures and lower wavelengths. And so let's say the blues and those kind of wavelengths are going to be refracted more, as well as colder temperatures versus the reds and the warmer temperatures that are going to be refracted less. So with these effects in mind, we can take a look at the Chicago skyline. these time lapses are filmed 60 miles away from Chicago. You can see the same effects observed during the Skunk Bay time lapse that we already showed. These buildings are relatively stable, but are brought lower by a combination of diffraction limit and the warmer air over Lake Michigan, both taken in the spring. So we'll play these time lapses and you can see this effect. You've brought these buildings lower essentially by a combination of diffraction and upward refraction. So we'll see the first one here. Again, the buildings aren't brought up and down bodily very much at all. They're somewhat stable. You just get this kind of, the water line kind of goes up and down a little bit here and there. Maybe the floors compress and expand a little bit here and there. You can see the haze of the skyline of the entire city across it. This one over here on the right, you can almost see the entire city of Chicago 60 miles away, just kind of lit along the water line. And you can see the Willis Tower and some of the other skyscrapers along it. And again, this is 60 miles away, which is around 2,000 feet of curvature. The tallest building is less than 2,000 feet in the Chicago skyline. So there's another aspect to this upward refraction that needs to be discussed as well, and that is the compression of an object and an apparent gain in observer height. So the greater the upward refraction, the greater the apparent height gain or horizon drop. Similarly, if there is rapidly dissipating upward refraction, there is compression of the lower aspects of the image. So we'll see these two effects, this apparent lowering of your horizon line and this compression effect of buildings and boats and so forth. So to see this, we can change our prism to a gradually linearly increase in density, or a linear increase in density like we've talked about before, and you just bring the whole building down somewhat stable. So what I mean by that is if you look at the prisms that I've put in here, you can see this gradual increase in density, and it's very linear and straight on the left, and that's going to essentially just bring the entire image within your view down by the dotted lines. Again, your eye, assuming straight lines, straightens out those lines and pushes the image lower. Or we can create something that starts off kind of low, but then increases in density rapidly, or essentially it rapidly dissipates, and you get let's say a lot of light bending early on down low, and then a lot less light bending higher up. So it takes on kind of a shield appearance, I guess. So what ends up happening is the light is bent a lot more at the bottom of this kind of a prism than it is at the top. And so the effect is that you see something like what happens on the lower right, where the light that you straighten out with your eye, that dotted line, is traveling a lot more than the light higher up along the building. So those two red arrows, the red arrow along the bottom is a lot longer than the red arrow along the top, between how far that dotted line has traveled to create that new image. And so in effect what you end up seeing is a compression of the lower aspects of the buildings, and or an expansion of the buildings along the top relative to them. So the difference between these two distances represents what is being compressed into what you see. Again, the difference between the incident ray in yellow, and the black dotted line. The greater the distance, the more that must be compressed into that space. So more of the lower floors are compressed relative to the top. So as an example of this constant gradual upward refraction, so going back, this is the one on the left here, where we're kind of bringing the entire horizon down somewhat linearly. You can see the effect in these two image comparisons. Essentially, you are viewing the observer position of a person higher than you actually are when this upward refraction occurs. So in this first example here, the person changes their height within the same time frame, which is on the left there. Same time frame, observer height changes. So within only a few minutes, this person goes from 14-foot elevation to a 9-foot to a 4-foot elevation, viewing the same object in the distance. And then in the second example on the right, they take a time lapse from the same observer position at a 4-foot elevation. So you can see at 9:30 a.m. there's more upward refraction, and then at 9:50 a.m. a little bit less, and then at 10:15 a little bit less. And the reason I say that is because the red line, which represents that inversion point of that inferior mirage, is much lower than the horizontal yellow line in that 9:30 a.m. photo, and then it gets a little bit higher and a little bit higher. And that yellow horizontal line represents essentially very close to the person's eye line, in this case the camera's center of frame. So if you draw diagonals across the screenshot, you can create that point where the center of frame is for the observer. And so you can see how the red line has this inflection or inversion point, and you can use the distant mountain as the inversion climbs to meet that point. But what's very interesting about this is a couple things. So first, when you compare the 14-foot elevation to the 4-foot elevation at 9:30 a.m., they're essentially the same. And you can compare the 9-foot elevation to the 9:50 a.m. elevation. They're essentially the same again. And then when they go down to 4 feet on the left, it's essentially the same as 10:15 a.m. when we have less upward refraction, which makes sense. They're now essentially at the same refraction level, which is at a minimal, at their 4-foot elevation. The other thing to note is that the lighthouse is somewhat lower in center of frame in the 9:30 a.m. shot in comparison to the yellow line, and it's brought sequentially upward as the upward refraction amount returns to baseline towards 10:15 a.m. So again, the pictures are essentially the same, and the reason is because you are viewing the world as if you are higher up. So this person who is at a 4-foot elevation within a time lapse is essentially viewing what they would view 14 foot higher with different atmospheric conditions. So the red vanishing line again is lower in comparison to the center of frame of the observer, which is again done by the yellow diagonals within the time lapse. The light you are receiving is the bent light version of light that a person at an elevated height sees as straight. So recalling how light refracts from warm to cold air, when we straighten the lines from the observer, they gain apparent height and see more of the building. They aren't gaining height though, they are pushing the visible world down. So I've kind of diagrammed that here a little bit. So you have, again, you have this warmer, less dense air below and this colder, more dense air above. And it's bending the light. It's an upward refraction from the light hitting your eye. And so if you let's do a building example here on the lower right. So when I'm receiving this light that's being bent upward as it travels to my eye from a higher elevation, or even from the same elevation or very similar elevation, it's bending upward to me, my eye. My eye brings that whole thing lower, which is the red dotted lines. So when I view that thing and I straighten it out, it's as if my eye gets elevated in height to meet that object. So as the red horizon and vanishing line, the start of the inferior mirage, which is that inversion point, approaches the center of frame, so as that red line in the time lapse gets higher and higher to approach the center of frame, there's less upward refraction. And this occurs during the time lapse because the tide is rising and the temperature difference between the air over the ocean and the air higher up is diminishing. They are getting closer and closer to one another as the air warms up within the day and the sun travels above. So as the air warms and the refraction lessens, the time-lapse footage from a 4-foot elevation starts to match the 4-foot elevation snapshot on the left. So that was an example of this kind of gradual linear upward refraction where we're bringing the entire visible world lower to view it as if we were higher up. But now we're going to talk about this rapidly dissipating upward refraction. So when we have non-uniform, rapidly dissipating upward refraction, we can still push the visible world down and appear to gain height a little bit, but we also see this compression phenomenon within what we're seeing, this differential compression of floors, so forth. So when this occurs, the bend is greater at the bottom of the image, near the ocean. So more of the bottom is being compressed into the same space as that above. The entire image may experience some loss that is pressed into the horizon, or it may not if conditions warrant good visibility. Lower kind of non-refracted wavelengths and a lower angular resolution limit. So again, recalling our building example, the rays towards the warm ocean air are being bent upward at a greater rate than the rays that are higher up. And so when that happens, the ray has to travel a little bit further when we straighten it out within our eye. And we're compressing all that information into less and less of a space, essentially. So in this example, this building is 14 miles away from a 6-foot observer height with a P900. If we assume an arc minute of resolution at 0.02 degrees, then we can calculate our loss just like we did in the part 3 as height equal to d tan theta. So height is equal to 14 miles times tangent of 0.02, which comes out to about 26 feet or roughly 2 floors. So the building is 12 floors. On some days the entire building has been seen because upward refraction is pushing the visible world lower in that regard. So it yields an apparent height increase as if I were higher up, but I didn't gain any height. I'm still viewing it at a 6-foot observer, but I'm viewing it now as if, let's say, I was 12 foot high or something to that effect. So recall that when we have uniform upward refraction, we view the world as though we are higher up. And you can see that here in the photographs. You have essentially 8 floors visible, and I've outlined them in yellow, within the greater lower floor compression example plus less upward refraction, because the horizon line is higher in these examples, as we'll show later. And then when you have 10 floors visible, you have less lower floor compression until you get much lower down. But there's more upward refraction. So in other words, you've gained a little bit of an apparent height by bringing the visible world a little bit lower. But you're seeing a little bit less compression from the bottom, and you're seeing more of the floors. So when this occurs, theta improves for the object you are trying to view because the visible world is pushed lower. Again, video link in the description. And so to summarize, diffraction sets the horizon like we've talked about once light passes through an aperture. And these compressive and altered horizon effects are refraction and occur prior to the light hitting the observer. So hope that's clear. So there are other times when this building has been viewed in entirety without any apparent refraction on an exceptionally calm day. On this day, the true building position is observed and it's higher relative to these refracted versions where the visible world is pressed lower. Again, video link in the description. The theta for such an image would be roughly 1/5 an arc minute or 0.002 degrees on this day. So the image we're looking at is on the left there. There's almost no floor compression or differential floor compression within this video. And you can see kind of what the conditions were when this was filmed. So on the lower right, you can see essentially a crystal clear day with no waves of almost of any kind. You see a nice mirror line of the clouds above, and the red arrow is pointing to what we're actually observing within this video. It's incredibly far away. So again, it's about a 14-mile observation from a 6-foot observer height with a P1000. So returning up to the 4 pictures on top, so those 4 pictures are different days when this same building has been observed from the same observer position and the same observer height. And so what you see is, and I've standardized the purple lines with another method, which I'll show in the next slide. But that's essentially the true eye line of this observer. versus what is seen in red, which is the apparent horizon line, which has been pushed lower and lower on these different days. And again, that's an example of that gradual linear upward refraction where the entire visible world is brought lower. But we can also see within this same footage this differential compression as well. And so as an example of that, look at the condominium picture on the bottom, and you can see that that top structure on top of the roof represents about 3 floors worth. And so when you compare it to the upper left footage, where it's that crystal clear, essentially non-refracted day, it represents exactly about 3 floors. But when you compare it to the other observations, that top structure represents 4 floors on one day, about 4.5 floors on the other day, and another 4 floors. And the reason is because, again, you're getting this apparent expansion of what's above and apparent compression of what's below. And that's because those light rays are traveling further as they're getting straightened out within your eye line for the information on the bottom, and not as much for the information on the top. So again, just like how we showed with the previous diagram, when the light ray is bent more, you have to straighten it out more, and you compress more of that information down to a lower point. And so all these floors are getting pressed and squashed together near the bottom because the light rays are getting refracted more near the bottom. Again, the water vapor layer is rapidly dissipating. It's not a nice gradual linear dissipation into a more dense air layer. It's kind of a rapid dissipation, and so you see this differential compression effect. So we can prove this upward refraction with the assumption that the clearest compression-free image, where the water temperature is virtually identical to air temperature with virtually no waves, is the most accurate representation of reality. So when we do so, we can use that accurate representation as a baseline from which we can compare the other images. And we can use visible landmarks to scale them and orient them appropriately and look for eye lines and apparent visible horizons and so forth. So this footage has been captured on several occasions near Miami, Florida. In early January 2019, footage showed crystal clear resolution, and the air temperature and water temperature were both around 70 degrees on that day. There was very little water vapor and very little temperature change. Refraction was minimal, and the visible world was observed with lower wavelengths since they were not refracted away. Theta in this case was very low, somewhere around 0.002 degrees, because virtually nothing was lost at 14 miles. In other words, we were viewing with very low wavelengths, and there was essentially no aberration, no distortion whatsoever, artificially compressing any information, and the resolution was outstanding. So we will use that footage, which is footage 3, which is the third picture in each of these examples, as our baseline, from which we will compare the other images, footages 1, 2, and 4 respectively. Footage 4 was taken the very next day after footage 3 was captured. So looking on the lower left photo there, we can compare these 4 footages essentially. So when zoomed out, there is a nearby tree line present in all the recordings because it's taken from the same observer position, and the camera height is the same at 6 feet. So when we standardize them all this way, we can use the landmark as a marker for the true shoreline and 6-foot eye line represented in image 3, which is going to be our baseline. So you can see where the shoreline is in comparison to the tree, and that's going to be our true distant horizon line, because that's going to represent about 6 feet high along the distant shoreline, which is our 6-foot high person at where he's taking the observation from. So when you do that and you place that against the tree, so you can see it's kind of that lower outcropping of the tree line, you can expand the tree to essentially be the same exact proportions within all the other photos, and you will see what the true shoreline actually is within those other observations. And you see that in all those cases, they were pushed lower. And so then we can then kind of blow up the same purple eye line to see how when this individual zoomed in and he saw all these compressive effects, what he was actually seeing with regards to the true horizon and the apparent horizon. So in image 4, on the right photograph there, which is the lower lower screen. So essentially you're looking at about 12 images placed together. So the 3 images on the top are zoomed out, zoomed in a little, and then zoomed in a lot more to give us that compressed building view. The second row is again zoomed out, zoomed in a little, and zoomed in more, and then it does the same thing for our baseline image, and then the same thing for our footage 4, which was captured the next day after that great compression-free, refraction-free day. So again, in image 4, the tops of the buildings are barely observed. Recall that mirroring represents the water underneath. And so to believe light refracts downward and looms up the image over a curve, you must believe that the refraction and distortion free footage in the third example is actually the false image. And the true image is, say, 1 and 4. Recall that we already compared those images and found them to have a large amount of refraction and compression within that top structure in comparison to the rest of the building. It did not represent reality whatsoever. So in summary, upward refraction presses distant items into the horizon and presses that lower horizon and apparent horizon line lower. And so video link is in the description to all these video captures, and this is some outstanding work by Red Pill Philosophy. So great work, and a lot of great observations that have come out of this. And I'm going to continue on with some of his footage as well to explain some other effects. So having upward refraction as a prevailing atmospheric effect on distant photography and videography over water makes implicit sense, because ocean water is almost always warmer than the air above. And the vapor that's given off translates into less pressure near the surface. So again, the ideal gas law can be summarized as density being proportional to the pressure divided by the temperature. And so low pressures and high temperatures make for low density. Snell's law governs how light travels between two mediums within different densities, and it travels faster when the medium is less dense and less refractive. So less refractive mediums would allow lower wavelengths to be observed, and thus the angular resolution limit would diminish. So in essence, you can resolve more when there is less refraction. And the reason that's important is because within this footage that was captured on this particular day, there's almost no diffraction observed all the way to 14 miles. You can essentially see the entire shoreline with almost no compression of those floors. You can almost see people or boats very near that distant shoreline, which is incredible. And so there is essentially, you're viewing the world with very bright conditions, very low wavelengths, very little refraction, and theta is essentially 1/5 of an arc minute because there is almost no loss. Now, as he panned away and started to look at even more and more distant buildings, you did start to see a little bit of dimming. The brightness was started to go down a little bit, and as you look through more and more atmosphere, you're getting more and more higher wavelengths. You're viewing the world with higher wavelengths and with less light, and so that causes theta to be breached. And so somewhere around the 16, 17 mile mark, you do start to see the 1 arc minute worth of compression or of diffraction of these objects, and further out you do start to see some compression as well. So, and that all that makes perfect sense for how this would work. So again, we're essentially seeing, we'll say closer up relative, at 14 miles, we're just seeing under perfect and ideal conditions, and theta is extremely low. But as we look through more and more layers of atmosphere, we start to diminish that ideal situation, and we get to a point where the light is just not propagating as much through the layers, and we're seeing the world in those higher wavelengths. So we also know from Abbe's formula that illumination is important to resolution, like we've talked about in part 1, and theta increases as illumination decreases. So with distance, we're essentially viewing higher wavelengths and in a less illuminated world. So taking footage 3 as our least refractive, most illuminated, most resolved baseline, we can see the effects of atmospheric density increasing with distance. In other words, the greater the amount the atmosphere we're looking through, the dimmer the object, and the more we see in the higher wavelengths, like we talked about. So diffraction starts to take effect more noticeably, and theta increases back to our standard kind of 1 arc minute worth of loss. So whereas at 14 miles we had almost no resolution loss, and theta was essentially 1/5 of an arc minute or less, when we zoom into greater distances, there's less light, and we are seeing with those lower wavelengths, or excuse me, with those higher wavelengths. And when this happens, we may see farther, but at the cost of the image getting cut off at the bottom, having hit the larger 0.02 degree resolution limit, which is a 10-fold increase. So as an example, this is the view of the Palace condominium in the footage. It is viewed at 17 miles from the 6-foot observer height. The angular resolution loss at 17 miles and a 1 arc minute angle of resolution is 31 feet. And if you compare the images, it looks to be exactly that, about 30 feet. We will confirm that finding with several other images, but keep in mind that an earth curve calculator requires this building to be lost behind 108 feet worth of physical curve, with downward refraction even factored in. So I've put that screenshot of the Metabunk earth curve calculator there. So again, here's the Palace condominium on the right. It's that structure with the triangular outcropping. In the top is the video footage, and you can see about 30 feet worth cut off when you compare that to a closer up skyline view. But again, 108, which is almost these 3/4 of this building or more, is supposed to be physically lost. And we're viewing this on a perfectly crystal clear day with almost no refraction. The air temperature and water temperature were essentially the same. So there is essentially no downward refraction, even if such a thing existed over bodies of water, which it doesn't. So as other examples within this same footage that it was captured, objects were captured up to 25 miles away, with cutoff amounts corresponding to 1 arc minute after around that 14-mile mark, when again those lower wavelengths were refracted out and we started to see the world in higher wavelength. So if theta equals 0.02 degrees or 1 arc minute, we would lose again 31 feet at 17 miles, 35 feet at 19 miles, and 46 feet at 25 miles. That's how the calculation would run. And in these images, we can identify 3 landmarks within this same image. So the first is the William M. Powell Bridge at 17 miles from Black Point, which is the observer position, where there appears to be about 30 feet cut off. The second is the Carnival Horizon docked at Dodge Island, which is 19 miles away, with about 35 feet cut off, or about 3 to 4 decks. And the third is the Carillion Hotel and Spa, about 25 miles away, where approximately 40 to 50 feet is lost. So within the cruise line, again, you can see the bow of the boat on the left, and it appears that about 3 to 4 decks worth is cut off from that boat. For the William M. Powell Bridge, you can count the pylons. You can see the apex of the bridge in the center photo and how it slopes downward, and you can count about 8 pylons worth. And when you count those 8 pylons within the closer up photo, you see that roughly about half the bridge is cut off, or about 55%. This is a 77-foot bridge, and this corresponds to a cutoff amount of roughly 35 feet. So again, this is corresponding almost exactly to a 1 arc minute resolution loss within the compressed lower visual field. So with this understanding of compression and upward refraction, we can see how an object can appear to sequentially drop off into the distance. Recall that as an object moves through more and more atmosphere, the light is refracted more and more. So if light is bent by a certain amount nearby, it's bent further out the farther out. So recall in our building example how the floors at the bottom were compressed more as the light ray experienced more upward refraction. Again, the greater the refraction, the greater the compression. So the Lake Pontchartrain Causeway, for example, in the photo there, which is essentially two parallel lines along Lake Pontchartrain, could appear to be something like this, which is being curved downward. So this view is taken high above the bridge within the colder air. The warmer air above the water is less dense. The light from the more distant aspects of the bridge are bent upward to a greater degree than the nearby aspects. So the observer assumes straight lines and bends the more distant aspects of this bridge down further, just like we dropped our mountain, just like we dropped the buildings, and so forth. So again, we can represent this diagrammatically here at the bottom in an orthographic representation. We have our colder air up by where the observer is, and we have our warmer air down by where the bridge is. And as the warm air or the light rays are traveling toward the individual from the less dense medium to the more dense medium, they are refracted upward to meet their eye. The observer then straightens out those lines to assume light traveling as a straight line. Within perspective, we rotate this bridge upward to meet our eye line, and we have a false lower horizon combined with a bent bridge. And that's exactly what we see here. The red line represents the false lower horizon, and the purple line represents what is likely the true horizon for this bridge, representing more as it would in the upper left photo, where we are taking a photo of it very high above with very low compression of our visual field, and a more accurate representation of what that bridge actually looks like. So this upward refraction from less dense medium to a more dense medium higher up is very common to laser light, like we've talked about, over bodies of water. So again, we can look at the power lines across Lake Pontchartrain as well, which are also commonly cited as evidence of curvature. But again, it's just upward refraction. So on the left image there, you can see where someone took a photograph or some video where there is essentially no upward refraction whatsoever, and this is a straight line shot along orthogonal lines within 1 point perspective to a vanishing line, which is represented in purple. And you can mark out where the orthogonal lines are on this photo, because the power lines from the bottom point of the observer all rise up to meet the purple line, and the orthogonal lines from the top all descend to meet the purple line, just like how we showed in part 2 how your perspective is formed. So you can determine exactly where that purple line is by finding the point or the orthogonal line that is neither descending nor ascending, and is the horizontal orthogonal line, or the horizon. So when we do that, we can standardize this purple line across 2 separate days and 2 separate observations. And you can see on the left there's essentially no upward refraction. Nothing is being bent down in the distant distant atmosphere. The horizon line is essentially center frame. And then when we standardize that to the orthogonal lines across the where there's upward refraction, we've again pushed the apparent horizon lower, which is what we've done in all the other instances. and we see this this bending as the atmosphere gets more and more. You're seeing through more and more dense layers. You're getting more and more refraction of those distant power lines, and the light rays are being more and more bent upward to meet your eye. You're straightening them out more and pressing everything in the distant horizon down lower. So I can blow up that phenomenon and expand it in the upper photo there with the red line, and you can kind of see how that's occurring. So again, with more and more layers of atmosphere, you're just getting more and more upward refraction. So what's interesting is there's a Discovery Channel show called the Stephen Hawking Genius Episodes, and a video link will be in the description, where they attempted to explain this phenomenon of this upward refraction as the curvature of Earth. So the laser was 2 feet above the surface, and it was pointed at a nearby boat for calibration. The boat then went 3 miles away, and they recorded where the laser hit on the boat. They saw it 6 feet higher and claimed that the water had curved downward while the laser remained straight, but the laser had bent upward and the water had remained flat. They flipped reality upside down and tried to sell bending water. So as you can see here, she is about 2 feet, possibly even 3 feet above the water line, and calibrating this collimated laser to this boat, and you can see it's hitting roughly 3 feet high, so it's probably roughly horizontal as it's leaving. That's fine. But then as they travel further out, you can see the observation, and you can see how this thing is being bent upward. And so he's marking this thing 6 feet off the ground and saying that that is proof that he has descended 6 feet below where the laser was, going down Earth's curvature. But the laser was just being bent upward over water. That's just what happens. So their version of reality is that the laser was straight and the water was bending down and they were traveling along it. But in reality, you just flip that around. The laser was bending up and the water was straight. Again, light is bent upward across water. So they also, I believe from kind of watching this whole show, that they were trying to match their observations exactly to what an Earth curve calculator would give them. So at 3 miles on an Earth curve calculator, you're supposed to lose 6 feet, but they didn't seem to take into account the observer height, which was about 2 to 3 feet above the water line. So they didn't really get that part right as well. They should have only lost maybe a couple feet at the most. But again, you're not even observing any of that. This is just upward refraction over water. So lastly, with the inferior mirage effect understood, let's look at another example of diffraction limit. The lid here is marked at 1-inch intervals. The observer height is 1.5 inches. The pictures are taken at 20-foot intervals. So this is a fixed height changing distance example as opposed to a fixed distance changing height example. And again, video link is in the description. So I've standardized the lid across the different distances, and where the inferior mirage effect, essentially this mirror zone, is taking place, which is a marker of where our horizon line is. And so when you do that and you line these images up from 460 feet to 100 feet and compare them, you see that roughly 1.75 inches has been dropped. So this individual put a ruler, essentially, with a piece of paper or a piece of paper acting as a ruler up against these two lids, and you can see that about from the 10 and 9 mark on the picture on the lower right, that those all represent an inch. So we've lost essentially 1 3/4 inch between these two photos when I blow them up, standardizing them across that mirror zone that is developing. So you can see when we match up the vanishing lines correctly between the 100-foot and 460-foot observations, we lose about 1.75 inches like we discussed. And again, the loss at 100 feet is essentially negligible here. And we can use this drop rate to calculate theta for this observer. So we'll do that here. So again, 1.75 inches is lost at 460 feet. We plug that in. So 1.75 as our height, and which comes out to 0.1458 feet across a distance of 460 feet. And so tangent theta equal to height over distance, and we get 0.1548 over 460 equal to 0.018 degrees, which is very close to, again, 1 arc minute. So using the loss to calculate theta for this camera within these conditions, I can now calculate the amount of loss over any distance. Alternatively, I can calculate the amount that is resolved with a change in height, because I know the theta for this observer under these conditions. So let's say I plug it in at 260 feet. I would expect a loss of 1 inch. At 380 feet, I would expect a loss of about 1.43 inches, and so on. If theta is held constant across any similar triangle, we can restate our formula as h1 over h2 equal to d1 over d2 would approximate h1 over d1 equal to tan theta equal to h2 over d2. So if you know the distance to an object and the amount that is lost across theta, you can calculate when the object would be completely lost. So for us, our 11.5 inch height lid completely disappears over the horizon at a distance d of 3,050 feet, or about half a mile. Alternatively, over a distance d of about 1 mile, or 5,280 feet, we would lose a height of about 1.65 feet given this angular resolution, or about 20 inches. So of note, if this lid were instead a 6-foot man, he would disappear completely at 3.6 miles within these particular wavelength and aperture conditions. As another example, you can see the effect more clearly here. This lid is marked at 1 inch increments and photographed 1.5 inches off the ground at various distances away. Some of the pics were downloaded at different levels of zoom, but you can see the effect on the lid. It disappears into the floor and the whole lid is brought downward. So we can kind of highlight some of these lid lines and see how they drop or essentially set into the lower horizon line. So I've outlined some of them in yellow, orange, and a little bit brighter yellow, and you can see if I pull out some of these pics as the person gets further and further away, you start to lose the brighter yellow altogether. It's completely lost within that lower horizon compression zone, and the rest of it descends as well. So let's summarize where we've been up to this point. So again, I want to impart to you that the loss of information at our horizon is an optical phenomenon. The ground is brought to eye level. Our eyes are not brought to ground level. Distant objects disappear by a combination of the angular resolution limit of the observer and upward refraction. So option 1, the ground is brought to your eye level. The person disappears from perspective, getting smaller with distance by walking straight away, vanishing bottom first, from again that preferential compression of that lower visual field as you are pressing those visual angles against a tangible object, in this case let's say a floor. When we do that, which is in the bottom example there of our 1-point perspective, you see that those lower transversal lines get more compressed and the upper transversal lines get more expanded. So when this happens, those lower transversal lines approximate theta a lot sooner than the upper ones do, and the object, as it moves straight away from you in a straight line, will appear to set into your horizon if it started out with parts of it above and below. If it started out completely below your eye line, it would disappear as a point because it never crosses above your eye line if it moves in a straight away. If it starts out with part of it above and part of it below, the part below will disappear sooner than the part above, and the part above will continue on until it completely sets within your lower horizon, which is again brought nearer to you. If the object starts out above your horizon line and travels straight away from you, it will appear to descend until it hits the purple, essentially eye line or vanishing line, at which point it will set. And so we've summarized that phenomenon here as h1 over d1 equal to tan theta equal to h2 over d2, or summarized as h1 over h2 equal to d1 over d2. So that essentially concludes our first four parts here concerning angular resolution and likely how we truly see the world. And we will now turn to our second option to see how this was manipulated to calculate the radius of Earth. Again, cracking these codes is collaborative. Special thanks to everyone involved and all the hard work that they're doing. So hopefully we covered the inferior mirage and the horizon, refraction effects across bodies of water, and we summarized angular resolution up to this point. So we're now going to turn to, in the next video, kind of the world we've been given, and so not necessarily the world that we observe. So we'll discuss a little bit about Airy's failure, axial tilt, and the human eye vertical field of view as a means to derive Earth's radius in one way, and then the derivation of Earth's radius by the extrapolation of the angular resolution limit of the human eye, and the derivation of the parabolic drop rate within perspective, commonly known as 8 inches per mile squared.